the conference and line arrangements. I don't think they appear officially in the conference title, but they're very much linked to Braids, and here's a picture of some line arrangements to show you what it looks like. And this is the kind of the talk. I'm going to start a little bit with a brief introduction to hyperplane arrangements. You already heard a little bit in Mario's talk, I think, a little bit. And then I talk about the algebras that being attached to do. So this will be more like a theoretical kind of discussion about how to use the algebras to study groups. And then I will return to arrangements and talk about this the algebras of the arrangement groups. And then in the end, I'll get back to Braids and the Braid groups and the variations of this welded Braid groups and virtual Braid groups that you also heard, I think, in the first talk, as they relate to virtual Braids and welded Braids. And I think we're going to hear about again Wednesday, right? Yes. Okay. All right, so that's the plan. So let's start slowly with common arrangements. These are finite collections of four-dimensional linear subspaces in some complex equivalent space. Sometimes we also allow affine subspaces, just lines in the plane. So the combinatorial object associated to hyperplane arrangement in the intersection lattice, partial of the set, ordered by reverse inclusion, and ranked by codimension. So the other way around. So, for example, this is an affine arrangement. Lines in the plane. So the lines are H1, H2, H3, H4, 4 lines, and there for multiple points, X1, X2, X3, X4. So these are the flats. This is the rank 2 flats. So this is okay. This is on the left side, the geometric picture, and here is the combinatorial picture, facet diagram. These are the points incidence, points and lines incidence diagram. The level 1, the rank 1 is codimension 1 by hyperplanes. The rank 2 are the codimension 2, which here are just the points of intersection. Okay. All right. Topologically, the main object associated with the complement arrangement is the complement. Okay, of the union of the hyperplanes. This is a smooth quasi-projective variety. It's also a Stein manifold, so it has the homotopy type of a finite connected L-dimensional serial complex. We are assuming here implicitly that L is true, right? All right, so here, a couple of quick examples just to set the stage. Very familiar examples. One is the Boolean arrangement. There's a code in hyperplanes. So the intersection lattice is just the Boolean lattice of subsets of 0 to the end. But the complements is just C star to the end, the complex algebraic close, the classifying space for the field of rank n. The next example is probably the most important one in the whole theory that connects Braids and arrangements directly is the so-called Braid arrangement, which consists of all that hyperplanes, Z equals to J. We saw them explicitly in Mario's talk this morning. Intersection lattice is the lattice with all the partitions of the set 1 plan, ordered by the final. The complement is the order configuration space of n distinct points in C, which is a spherical space, is a K by 1 for pi equal to pure Braid group on n strings. Right? So remember all that from Mario's talk. This was also his motivation for this talk. K by arrangements. All right. So again, this is all review, but that's why my title. If I go back to my title, I said open news. So I'm gonna spend some time here injecting and doing some review of this material. But not everybody is familiar with, I assume. So the homology groups of the complements are finite, of course, because it's a finite serial complex. but they're also torsion free. And the ranks, which are just the Betty numbers, are given explicitly, well, explicitly by this formula. Left side is the Poincare polynomial of the arrangement, and the right side, well, it's again a polynomial, where here these are the ranks, this is for the measure of the flats, right? Here we take the sum over the flats, and here you have a modulus function associated with this concept, which is defined inductively at assigns to the bottom of the rank 0 group for dimension 0, which is the ambient space, the value 1, and then we go level by level. The hyperplanes would have value -1, and then you just go through the lattice and compute this modulus function, and that gives you the Betty number. So this is a very kind of coarse combinatorial information that gives you the Poincare. If you want to do something more ambitious, in fact, compute now the actual ring structure, the Kappa, the homology of the Hamilton arrangement, that also can be done. This is a celebrated result that goes back. It was initiated by Vladimir Arnold and this paper on homology of Braid groups. He did it for the Braid groups, and then carried out orbital arrangement by Griswold. And then it was reinterpreted by Olik and Solomon in combinatorial terms in terms of intersection lattice. So, namely the homology link with integer coefficients is the external algebra. The external from the degree 1 classes, each dual with the meridians are on the hyperplanes. We just talked about these meridian curves where they transverse this to the hyperplanes and they do circles there and one of them a base point. So these are these meridian classes, dual meridian classes, and so these are the generators of this algebra, and then the relations are defined in terms of this lattice, and the information for the lattice by computing this differential, which on the generators pH takes the value 1. And then you extend to the whole algebra by the digit level. So I'm using also this shorthand for a subarrangement. These are the parameter relations given by this formula. Whenever you see something of dimension less than expected, it's not in general position, then you get a relation. Fine. Okay, anyway, so that's the horizontal algebra. I won't say too much about this today. This is more like in terms of background to tell you what's known. This is up to 1950, 60s, 70s, 80s. I'll tell you more about the fundamental group of the complement. So in order to complete the fundamental group, it's enough to take a planar section. So we reduce to a planar problem, take a generic planar section, then the arrangement group is just as the arrangement of the complement now is a fine line arrangement, the complement of this, so you can just reduce to this equation in this picture. There's a bunch of lines in the planes, nothing deeper than that. So this is by kind of a Lesch's happiness section type of theorem, but in kind of a singular case, we do have in there. We can do that. It's obviously. So here, by taking this arrangement of affine line CC squared, I kind of rename this A, take a generic projection to move from C squared to C, then you get a so-called Braid monopony. Associated with this line arrangement. So yeah, I think we've seen this before, maybe Moshe was talking, or maybe it was during the weekend, or, also kind of was mentioning. So you get a diagram like that, basically kind of flat this arrangement in this picture, and you can see now some braiding that occurs in between, but then these are singular braids that intersect in this multiple points. So that's a pretty wide diagram associated with that picture. Or kind of flattening on the plane. And from that, we need a bunch of braids. We get these local braids, alpha 1, alpha x, where s is a number of multiple points, and the 4 before. And these braids are not any braids, but they're actually pure braids. They begin and start at the same time. Well, they use the presentation. You understand? And so it's a group that it's a fundamental, it's sort of like the presentation you get from the fundamental group of the complement of a node of linking S3 by this method of acting. But instead of having there, we're using this Alexander theorem, I mentioned this morning, you take a single braid that blows up, and then you have just x1, xn, modulo this relation, the xi equal to the braid applied to xi. Here, you, instead of having a single braid, like in the case of nodes and links, you have a bunch of braids. But except for that, it's the same type of presentation. Fair enough? Simple. No, okay. You notice that. Okay, so I won't say more about presentations. Just to kind of emphasize that, again, the generators are Arrhenians, and the relations are all commutative generators. Why is that? Because these are pure braids, alpha j, so they send an xi to a conjugate of xi itself. An arbitrary braid will take an xi and send it to a conjugate of an xj. So this will not be commutative in general for an arbitrary. Because these are pure braids, these are actually in the commutative subgroup of the three component matrix. Okay, and I'll come back later on to this point. Okay? But this will be important. Pretty much all we need about it. Okay, so that's my quick review of arrangements. Let's go now do some classical group theory. This is a kind of the lead method in group theory, as they call it, in some quarters. I mean, it was started in the 1930s, I would say. In England, the German field call, and then we Ernst Witt in Germany, and Marshall Hall. But then it really picked up with Magnus. Magnus was the advisor of John Berman, right? And then it was picked by the Russians. So that was very popularized in Russia, mostly in the 50s and 60s. Okay, and for a while I think it went dormant, but I think it kind of it had a certain kind of renaissance, this method. And part of it because it appears in this theory of particle arrangements, and also, of course, in the theory of links and knots. Milnov started in the 50s. So, okay, anyhow, so that's the method. And what is this? So I start very general with a group. We take the lower central series, define again inductively. Gamma 1 is G, and then gamma 2 is G comma G, gamma 3 is G comma gamma 2G, and so on. And what is this comma? Well, I mean bracket. So gamma 2 is the bracket of G with G, which is the commutator subgroup, right? So more generally, you have two subgroups H, K, and G. The bracket of H and K is the subgroup generated by all the commutators. You can elements in H and K, right? So it gets smaller and smaller, right? It's a descending series. The terms of the series are normal subgroups. In fact, they are invariant under any automorphism. In fact, any homomorphism in groups takes one series to another series. And crucially, it satisfies the so-called multiplicative property. The bracket of gamma k with gamma L is gamma k plus L. So if we take brackets, we will get deeper and deeper in this lower central series. In particular, the first one is gamma 2, which is just a direct subgroup. So the first quotient, G bar gamma 2, is just a diagonalization. Now, in particular, if you look at this equation with L equal K, you get gamma K is inside gamma K, so it's actually gamma K plus 1. So this is actually, because of this, the LCS quotients successive quotients of the series, gamma k minus gamma k plus 1, that can be known by GR K of G. These quotients are actually abelian groups. Okay, so that's a pleasant feature of the series. And finally, on this slide, if G is finitely generated, which for practical purposes in this talk we will assume that it will be given these things like Braid groups and arrangement groups, they're all finitely generated. Then all these quotients are also finitely generated, so these are finitely generated groups, so it makes sense to talk about that. So this is some numbers, pk of G, associated with a group. Okay, so every finitely generated group you can associate in a factorial way this series and these quotients, and you get a sequence of numbers associated with the group. Right? So it's an interesting question. What is that sequence? If I give you a group, complete the sequence. Even for a finite group, I give you the same computer, the sequence of numbers. Right? Computers can do that up to some point. Okay, but that's not, I mean, what it really makes it interesting here is this extra structure that I want to emphasize is, okay, first, we can expect, generalize this a little bit by also putting some coefficient in K, for example, K equals 0, K field. So you make this, right. So here was just a single quotient. So you package all these quotients into a single object. This GRG, which is the summation, the direct sum of this GRKG, right? So if you don't have K, this is just a graded ability. Okay? It's like when you find homology, you find one homology to after the other, but you know, really we want to study all of them at once and make a graded object. And like in homology theory, sometimes it pays off to pick up coefficients. That also mimicking something. It's very standard algebraic topology. But okay, so that's the object. But what is like in homology? You want to have some extra structure. Right? That's in homology is co-algebra, but that's not the homology kind of brings them, right? In this associated graded algebra, the extra structure is that it comes actually endowed with a Lie bracket, a graded bracket that goes from GRK across GRN to GRK plus. And what does it come from? It comes from the group commutator. If you think of an element here in GRK, and then you take it represented by something gamma K, something gamma L, and you take the bracket. Remember, it goes into here. I'm using this fact. The bracket of gamma K is gamma L, K is gamma K plus L. So when you pass to the quotients, you get this operation like that, right? That's just because of that. But then I think this is the computation goes back to Philip Paul. I had to do the research because I have two British mathematicians. They did at the same time, do the same kind of research almost. But one is Philip and one is Marshall. Okay, so this was done actually by Philip Paul, right? And then we showed that there are these kind of Paul, sometimes called Paul the Crespo kind of identities. On Paul with identities, they are satisfied by these commutators, and then when you pass to this bracket, they satisfy the Jacobi identity and the Stupon identity. So this is really the algebra. Over Z, we work with Z coefficients, or over K, for this three coefficients K. Okay, and again, this is factorial, and in G is not generated. This graded algebra is finally generated. So the classical example, the first example in literature, when this was fresh in the 30s, was what about the free group? Okay, and the first term of the subject, I would say, besides the setup, was the fact that you take the free group and you take this associated graded, you get a free graded Lie algebra. Okay, so it takes three objects. I think this was Magnus, and then actually the ranks of these groups were computed in terms of now the classical Braids function associated integers with a lot is given by divisibility relations. So these are the ranks of the LCS quotients of the free group, which are the same as the ranks of the linear. Okay, so far so good. All right, I'll take another variation on the theme, which I like quite a lot. Is the chain algebra that kind of combines this idea that I just described with some information coming from another series of a derived series. Okay, these are the two main descending series of the group: lower central series and the derived series. They're both based on the idea of commutator, and they both start at the same place. Although there is, I know classically there is a shift of one. Okay, so this starts at G1 with G prime, and then G with G double prime, just because this mimics, that they're taking derivatives. Okay. See, the other one started at the G1 was G, right? You see that? Gamma 1 is G. Here, G0 is G, and then G1 is G prime. All right. And here we take not G comma G prime, we take G prime comma G prime equals G double prime. Okay, so just like something slightly different. And the quotients are the quotients are solvable. And for example, G mod prime is the maximum meta-abelian quotient. G mod G prime is the maximum abelian quotient. Next one is the maximum meta-abelian quotient. Anyhow, so now what is the chain of the algebra is the associated gradient of this solvable, maximum solvable quotients of G. The factorial, the projection, just surjections between G and G multiplied by I, and you get an isomorphism up to the degree 1 and so on. Let's not spend too much time on that. So again, assuming G is finitely generated, let's look at the ranks of G after G over time. Call them chain ranks, because G over prime is a quotient of G. You get this inequality between these two ranks, and because of this theorem, I just kind of stated here above, which is very easy to prove, you get an inequality out of this three. So the first three types of ranks, phi1, phi2, phi3, phi1, phi2, phi3, but from 4 on, they start diverging.
Can I ask you what do you mean by prime here? G prime and G double prime?
Well, G prime is just G prime is just the derived sum, right? No, I didn't say that. Well, it's here. G prime is. Oh, I should have said here. I said it was G0 is G. I said it was that it was this one.
I do. Okay.
I have to say that the series starts, right? Okay, so why Chen, actually, so this is, you may have heard me say before, this is, so Katie Chen, the topologist, he came here at Columbia, was a student of Sami Island, right? So there was his thesis that he wrote. And in his thesis, basically, that's what he did. He defined this Chen algebra and did this computation, computed the Chen ranks of the free. And it was published in the Annals. There was a golden base of topology, pretty much of any kind. Here's a little paper, boom, the Annals. No longer, those were the days. Well, because Fox was there, all this, so they kind of realized it and some they control the Annals. Anyhow, so it's a nice computation. It's a bit of a binomial. So
But that's not what he is most known for.
I know that he did then I'll come back like Holomid algebra. We did what do you know him from? Path integration, loop space, integrals. He's also he was the advisor of Henry. So I mean,
but he's still, in my humble opinion, mostly known for the iterated integral.
You're right.
Not for the big chain.
But that was his humble beginnings at this thesis when he did this computation. Okay. All right, so that's another construction, also the loop chain. But years later, maybe 20 years later, in the 70s, 60s or 70s, the following the algebra. So this is a different construction, and it says, in a sense, it's more simple-minded and more down to earth. It does not use the group structure. It just uses homological information extracted from the group. It only uses the homology ring, the classifying space of the group. And you can actually do that with you don't even need a group. All you need is an algebra. Okay? It can also be done for differential graded algebras, all sorts of variations of this thing. So basically, let's first do our filling here because it's a bit easier. We take the free algebra on the on H1 of G is K coefficients, which just means G times of K, and you model by a certain idea the image of a certain linear map. Okay, so let's kind of decode what this means. So let's write L to be this D algebra on the vector space V, right? V is just H1 of GK. Now, remember what this free algebra is. Degree 1 is just the vector space. In degree 2, the free algebra is just V wedge V. Okay? To identify X bucket Y with X wedge Y. That's a homomorphism. And now you can have also remember this kappa, right? H1 wedge H1 and H2. You take a dual, the transpose basically of this map, and then you get a map from H to GK to V wedge V, which sits inside L2. So you can take the ideal generated this image of this, I'm gonna call it homomorphification. Okay, so that's the free algebra. It's just very simple construction that basically just linear algebra construction. Don't use computer calculus or anything, read brackets on some complicated stuff. Done more like a standard algebraic construction. You can do it over the integers. The only thing is you see, you take in here duals, you identify, and okay, anyhow, for various technical reasons, for example, because I want to take, I need to use universal coefficients here in the right way, I'm going to first model by the portion of each one, and then I take the group. So, okay, so then by construction, this three algebras that I just told you about, are also functionally defined, and are graded the algebras by construction. There are portions of the free algebra where homogeneous ideal is a quadratic ideal, sits in degree 2. So this is a quadratic algebra, and if G is finely generated, so are these the algebras. So for example, for the big group, you get again just the free algebra. If G equals Z to Cn, you get Z to Cn in degree 1. Okay. Now, what is a relation? So this is, and again, I think, yeah, over Q, this was done by Chen, in that paper, maybe 16. There is a natural surjective morphism of the algebras from the Holombi algebra to the associated algebra, which in degrees 1 and 2 is an isomorphism, but in the higher degrees, it's, can have a kernel. If the group is one formal, okay, so that will concept, if I ever explain all details of taking a long time, so I just leave my hands. Basically, out of a group, we can form its quantipotent completion, also called the multi algebra construction done by Quillen. Okay, but it goes back to Maltset, and that's now this is a filter of the algebra. Was associated graded with the associated graded algebra of the group. Okay, so there is a whole theory about this quantipotent completion of the group. And if that Maltset algebra is quadratic, that means a quadratic representation, then we say the group is 1/4. Although there are many other definitions. Okay. Anyhow, in that situation, that I will come back to, For example, all arrangement groups are formed. Okay. Compact element, fundamental groups of compact element. And so there is a wide plethora of formal groups. Normally speaking, I mean, very loosely, very informally speaking, it means there are no non-trivial massive parameters. So, for example, three manifold groups are not as far away from being formal. They have all sorts of massive parameters floating around components, but arrangement groups, tether groups, and so on are formal. In that situation, rationally, this map is manifold. So it kind of gives you, in such a pleasant geometric situation, a way to compute the associated gradient in terms of the homology measure. Which normally shouldn't be very surprising, because what does it mean to be formal? It means basically that all the information that you need in order to build up the rational homology type, to understand the rational homology of the space, is encoded in the homology ring. So here you say, in order to understand not the group itself, a type ring, but its associated with the algebra is built into this. The algebra becomes type explicitly from the homology. Okay, so here, here is an old result of the token. I'll come back out. You may have heard this name kind of in connection with hyperplane arrangements. This window for characteristic of arrangements. I'll come back to it. So in his study, he made some kind of statement, but there's no proofs and not very well. Say finally generated. I think I forgot to say keyword here. And torsion free. Any torsion free. So finally generated and torsion free. So then I don't have to modify the torsion. I just get this map H to G to GR where GR. It's objective, right? This map that we just talked about here before. This map. Mu G dual, but then with Z coefficients. Okay. So if you put this assumption, also that it's torsion free, then you don't have to modify the torsion. But in general, this map is not injective. So if it's injective, then the map between H3 and GR3, the first mysterious level is H3 to GR3. This map is an isomorphic integral. Okay. So that's kind of the only thing. I mean, after that, if you go to 4 and so on, it becomes more and more mysterious. But at this level, this happens. Okay. All right. So that's a general theory. Let's go back now to arrangements. So that GB arrangement. Okay. So remember, it has a finite presentation with commutator. Okay. So the generators are the meridians basically, and then the relators are all in the subgroup. Let's call the homology algebra just H of A. Basically, now putting together the orders of, if you look at the horizontal algebra, the relations in that algebra, and you take some duals and use some linear algebra, you get these relations in the homology algebra. Is the free algebra on the meridians modulo these three brackets. So how many of them are there? Well, you take for every rank 2 flat, right? So meaning if you look at, you just have to look at this kind of value, right? There's multiple points and lines. So you look at the multiple points. X, right? And for each of those, you look at the lines going to the multiple point. And for each such pair, you get the relation saying that XH, the here 1, 2, 3, H1, H2, and that is multiple point. It says that x1 commutes with x1 plus x2 plus x3. 0, right? And x2 commutes with it. And x3. Okay, so for the triple point, you get in principle 3 relations, but one of them is redundant. So that's why I said no, we accept that. But anyway, one of them is redundant, and here because x1 bracket x1 equal to 0, you just get, you simplify this to something. You get this here later and this. Okay. But you have a double point, you get 1 and 2 meeting, you get x1 bracket x2. You get a triple point, you get, so you can take these two, right, for students. Project and give a binary, rather than this algebra, put in a computer and things, in computer ranks, computer. I come back and there are open questions. That's all we have to know. Just write this. You have to be opposed to the reasons. The project. And this presentation only depends on, actually, the first one was this presentation, really sector stack. I think it was Toshitake Kono, 1983. The paper in Nagoya. But, it's not different. So this is a presentation that depends only on the first two levels of just the points and points. In degree 1 is just the idea or rank that. And rank 2 is a simple exercise, and this is the basis for H3. And I don't know what H3 is. Very, very good question. Dozens of papers on it. Maybe not this title, but along these lines. All right, lower central series. So, arrangement groups are formal. That basically goes back to Briscoe. Although Briscoe didn't know the notion of formality, it was not formally defined. It was only 77 by Sullivan, but basically showed that the RAM algebra splits back into the cohomology ring splits back into the RAM algebra, which is a very strong form of formality, which for the Braid arrangement that was done by Arnaud. These are the famous Arnaud relations that called for Braid arrangement and exactly the same relations, with no branch, no pulse in the relations hold on the nose in the RAM algebra, the one that can be back on. So that's a it's very strong form of formality, but it's proved using the RAM homology. So this uses real form. So it's formal over real, which also means it's formal over rationals. And shown. But on the other hand, arrangement groups are not formal over finite fields. So although they are very strongly formal, all the massive factors vanish, but not rationally. There can be, and there are non-vanishing massive products, which creates all sorts of problems, and a lot of them behind the scene. What makes this so difficult is the lack of formality characteristics. Anyhow, so because of this formality, rational formality, this fact is an isomorphism between H and GR, as I said. So the ranks, the LCS ranks, depend now because this is the same as that rationally. So the ranks depend only on this intersection, like this 1 and 2. But just knowing that that's combinatorial doesn't mean you have a combinatorial formula. And again, this is something which is not known. Although it's been studied. This simply is my fault that Toshitake Kono and others started this for the Braid arrangement. The tables in concern assess the LCS ranks of Braid, which Yeah, this was one of my papers. This paper in the case when A is super solvable, for example, if it's a reflection arrangement. Like B, the Braid arrangement, like B, but not in general, not all reflection arrangements. Kind B is not super solvable. And then given by this one is B1 BL that appeared in the top of Mario, right? In other words, this similar product extension, these bundles, right? They're the bundles with fiber C minus a bunch of points. These are this X1 and B1 BL. So knowing how many points are missing at each stage of this iteration gives you these log and CS values. Okay? But that's a very, very special situation. In general, you don't even know what phi3 is. Okay, so one of my early papers, which Stefan Papadima convinced me to look at arrangements, we kind of started working on this research in person over 4 or 5 years ago. And the research in this paper on changing algebras, and we showed that for, in fact, more generally, anyhow, we put the general theorem about the chain ranks of one formal group. In particular, we showed that for arrangement groups, the chain ranks are combinatorially determined. But again, what is the exact formula? But in that case, actually, before the paper appeared, I managed to at least have a educated guess what it should be, and the conjecture 10 years ago. Again, because let me not say more than that. I mean, there is a paper where this conjecture is proved, but I think a proof with all the defects is still missing. Okay, so still working on it. Let me not say more than that. But anyhow, just to say that this now gets into the computation here gets pretty much 100% into a real more of computed algebra and algebraic geometry. The methods of computing now these chain ranks. Once you know this is combinatorial, you will do some further translations, and it all becomes a question of syzygies, some resonance varieties, and comparing some geometry with varieties to some. Number of syzygies in a certain resolution. Okay, let me not say more than that in this topic. Now, another thing you can do is this lower central series quotient, with this lower central series iteration of the is not just take the LCS quotient. You can take the quotient of G itself with gamma k. Okay, so these are called the important quotients. These are important groups of like G mod gamma 2, that's just organization, it's just a one-step important. The G mod gamma 3, it's a two-step important, and so on. The first interesting important quotient, G mod gamma 3, that's completely determined by the first by the intersection lattice. It encodes basically in a different way the homology link, this 1 and 2. But G mod gamma 4 is a much more complicated object, and this is what I alluded to this in the paper of reading of was I think a student of Gelfand. In 1994, he showed him by produced a pair of arrangements for which these two quotients are not isomorphic, so the groups are not isomorphic. But the paper was kind of languished. It appeared only in print only in 2011. And then this many years time to explain, and okay, I'll come back to the history, why what's the difference in terms of massive products. So it's still not 100% clear, what is a good way to explain the difference. All right? But let me show you kind of a different way to find arrangements I think Moshe told them is the same combinatorics, but different topology. I don't really like that terminology, but all right. Using this homology algebra, the ideas that I just discussed. So remember, GR is equal to the number of lines. Because this is this is also injective because the homology it's a portion of the external algebra. So the dual map of that surjection now becomes an injection. So the hypotheses are satisfied. So by the theorem that I mentioned of H is GR. Okay. I don't know whether it's the technique torsion. Okay, so that's I didn't put this on the board, but I just say. So all I can tell you is that they are the same, but there could be torsion. I suspect there is no torsion, but I cannot really make a conjecture. Okay? Let me just put it as a question. But on the other hand, here is a question that I posed. So I made a follow observation by computer, doing computations. Computers, I realized that the associated graded groups or arrangement groups may have torsion starting from the E5. I couldn't detect anything in the E3 or 4, but in 5, and the first such example thing is the MacLean arrangement. So in GR5, all of a sudden I can see some 2 torsion and 3 torsion. Okay. So that led to the question that I posed at the time. Is the torsion that appears in these arrangement groups is combinatorially determined? Okay. So that's much easier conceptually than doing this G-mod G for the way you go. Right? You know, I think I have a presentation to do that. K invariance, massive products, it's kind of a mess. Okay. So, but at the time, I don't know, I just didn't have the fortitude to run and I didn't have a database of arrangement. All I do is maybe compute up in mind. Mina was saying that we have to go to much higher, or maybe Sergey was saying, we have to go to 200 or something. But I kind of really have to go to about 13 because that's what we need of arrangement at 13 months. Okay, so I was kind of, you know, my network my computer kind of broke down after 9 and 10. But anyhow, about close to 10 years later, these guys, Akamato and Vallejo and USOS, answer my question. Actually, they went for database. Now they're much larger, computers are better. So they went to 13 lines and they found a pair where actually they found it at GR4. One has 2 torsion, one has no torsion. So these arrangements are 13 lines. Rhythmic has only triple points and double points. These have 11 triple points and 2 double points. So they have kind of higher multiplicities than the rhythmic arrangements. But on the other hand, you know, and it's also what makes them easier. I can say that they're defined by real equations, which is much easier to handle. You can write this Braid representation, you know, by formula. A complex case, it's a delicate computation, and it's prone to errors. Yeah, but thank you. I mean, that's also my objection. It's a computer computation. So what's missing, and this is something that I'm working on, is a conceptual proof where this happens. Okay, so what we need is developing with Suciu and the sequence of papers we're writing. We try to do minimal model over the integers. What Sullivan did over the rationals, tried to do over the integers, we kind of encode also the stimulus operations and massive products in characteristic P and torsion in the LCS and all this kind of stuff in order to try to understand, motivated by this type of examples, like typical and this kind of examples. You need some kind of integral motopic theory, not just rational motopics.
So this first one, up here, is it easy to construct this first one, or the kind of another expression of
the I think they produced like a couple of examples. I mean, it would be easy. I mean, there is a database with how many, maybe you know better than database. How many arrangements are there? Up to 30 lines, 200,000.
it's, I mean, by African.
Yeah, but then, it's smaller than number of, smaller than number of leaves. And you just run to the database and press a button.
All the experience. Can you tell that?
Well, I think that's maximum.
Okay, so, yeah, I need to sort of share that. My time is limited, so sorry, I need to I want to get through, I still have 9 slides. So let me tell you on the other hand, so that's kind of there is a large class of arrangements where the situation will, again, can give you a positive answer, where things work out nicely. Okay, and these are called decomposable arrangements. And again, this came in, okay. Let me first tell you the definition, then I'll do some discussion. So for each flag, we talk about for each flag, we look at the hyperplanes that contain the flag, also called the localization of the arrangement. Okay, so if you have a multiple point, you look at all the lines that go to that point. That's a sub-arrangement. So you have this inclusion, gives rise the other way around between complements. Okay, so the component of the big arrangement, you take more stuff out, so it's included in this less stuff out. So if you restrict to rank with flats, you get a map between the complement and the product of the components of these tiny little arrangements indexed by the rank 2 lattice. And then you look at what happens in fundamental groups. You use map between everything is factorial, so you get a map between the following algebras. Okay, between the big one and the product of the little ones. This one you can understand completely. This the local arrangement for rank 2 is just plus one bunch of lines. The group is the free group on n minus 1 that is Z. Is a fundamental group of the complement of the top, which is the closure of the Gaussian square, data square. Okay, so that's completely understood. And then everything here as well is product. So the right side you completely understand. So that gives you a comparison map between this quantity you don't understand and the one you understand completely. So in the paper about 15 years ago, about Ima and I will show the following, that this map is always a surjection, starting with degree 2. Degree 1, this is much bigger here because you're overcounting the number of lines. Okay, so in degree 1 it's hopeless with the isomorphism. But from degree 2 and higher is a surjection, and in fact the degree 2 is an isomorphism. So the crucial degree, that's where is degree 3. What happens in degree 3? So we focus on that, make a definition. We call an arrangement decomposable if this map in degree 3, H3 or H is an isomorphism. So in other words, the LCS quotient in degree 3, the third LCS quotient for the third holonomy piece, the third graded piece of the holonomy algebra is as small as possible. You have this lower bound here, this is projective, and you have as few elements as possible. Then we call the arrangement proposal. So anyhow, there were some precursors. I mean, this idea of looking at phi3 and getting a low band at the back of the lower bound came up in early work of Mike Fall. Then I studied this with Dan Cohen and with Hao Shang. So I had all sorts of technical considerations and results about something similar, but this is actually the stable definition of this class of arrangements, which, by the way, for those of it would be nice to have a definition which is kind of intrinsically combinatorial. Maybe Bruno can tell us, from matrix, what does it mean? I mean, you can define this holonomy, you can define the holonomy algebra for any matrix. You like matrix. You like the arguments, right? You like the matrix. And like saying, let's say matrix is decomposable in this map, certain linear algebra map is isomorphic, it's an isomorphism. Given an explanation, surely that's what the matrix. I've been asking this question. Brad has a code. It's the head of a package called arrangements. You press a button, that's all computations, and there's a button that says is decomposable. But I point you at the hint that that package is kind of it's it's not really correct because you have to, it fixes the characteristics. So it says this is an isomorphism in a certain characteristic, it does computation of a prime P. But this condition is over all primes. It has to be intermittent. So, it verifies that, one prime at a time, that what happens to the time, 101. Anyhow, so they never corrected this package. So the package that it quotes this paper, it doesn't really the computation the way I want it to be done. But it's better than nothing. Okay. So here's the theorem, kind of an old theorem. So we show that if the arrangement is decomposable, then the map, once you know it's an isomorphic degree 3, it's an isomorphic in all degrees, right? If there is no discrepancy degree 3, then you get a perfect match in all degrees. In fact, the derived subalgebra means, degree 2 is higher, this derived subalgebra is isomorphic to this product of the subalgebra. The map between H of G and G are isomorphism. And the groups are, there is no torsion. So in this class of groups, there is no phenomenon, like I said, this having torsion or having, anything kind of complicated like that. Everything works very smooth. It's still left the open question: what about this phenomenon that technical tests, right? You have arrangements that some important quotient is different, although they have the same combinatorics. So that's a much more result from last year's reporter, where we strengthened this theorem and showed that if they're incomposable and the intersection is isomorphic, you have 1 and 2, then all the important quotients are isomorphic in all degrees. So that's the total opposite of what typical is, right? Of course, these arrangements are not decomposed. But don't think that these decomposable arrangements are trivial, right? And the groups are not products of the groups. They can have all sorts of complications in themselves. Okay. Like, for example, not having finite homological dimension. Okay, so they may not have a finite dimensional K by rounds. Okay, so don't think this is a stupid class of arrangement. The group here gets very complicated. But when you pass to the algebras, the quotients, it becomes much simpler. Okay, so we have last 10 minutes. Talk about Braid groups. Okay, so this is a diagram I want to explain. So if you kind of stop paying attention, you can sort of wake up now, smell the roses, and look back at the board. Okay, so this is a diagram involving Braid groups and all sorts of related groups, related Braid groups. This is the most familiar one. I talked yesterday to the random undergraduates, right? This exact sequence P and B and SN appeared also in microscope and I think other talks. Everybody talks about it. We cannot even talk about Braid groups without talking about this exact sequence. But there are some other kind of related groups here, V for virtual and W for welded. On this slide, I'm going to explain. And then on top, floating around, there is also kind of the analogy. The Braid group is kind of has something to do with the automorphism of the free group. This is the IA, the automorphism. This is the homology, the Corelli subgroup. And this is the general linear group. So there is, okay. This is just a partial view of all the groups that are involved in this business. Okay, there are more groups like that. Okay, well, let me explain a little bit this diagram and tell you more about some of this. So the Braid groups, well, they're dealing with the Braid group next thing. This is just a short review. It's a matrix group of the disk with mark points. I want to emphasize this. I don't think this will talk with the undergraduates. That actually the Braid group is the sum of the automorphism of the free group. And it's characterized by the following. I mean, that's clear, right? You get the strings and then move these points around. So they give you an automorphism of the free group, basically by construction. But by inspection, also, this is due to Arthur, one of his papers. Also, all these papers about Braid groups are very balanced. The generators go to a conjugate of a generator, like I said before, up to a transposition here, coming from the canonical map from the FL. But also, this is because you take the mapping class group over this with boundary, not just the mapping class group of the plane, convex line. The braid fixes the product of the generator. And the random bit theorem of Hartman says the converse is true. If you have any automorphism with a free group, satisfying this condition is basis conjugating or braid permutation, right? It's send every generator to conjugate another generator and fixes the product, then it's an element of the braid. Anyway. The pure braid group is the kernel of the natural projection, the subgroup of IN, we use the identity of homology by construction. It's a literally symmetric product of free groups. Okay, at each stage you do an extension, and this is given by this active representation that thinks views Pn and the subgroup Bn, which is included in all the effect. And this is a classifying space for Bn. Pn is this complement of the braid arrangement, and for Bn the quotient by itself, and the complement of the sphere. Now, welded braid groups. Now, the welded braid groups, you kind of simplify the definition of the braid group. You drop this normalization condition. Here you have this condition. You drop this one last one. You just say that beta takes each x side to a conjugate of another. So that's a welded braid group. All permutation conjugate automorphism. So it goes by various names. But let me use this name. So, and then you have the welded pure braid group, which is there is again a projection percent either that, or you intersect this IM with WBM. So this is the pure welded braid group. McCool, I think James McCool, a mathematician, in 1986, gave a final presentation that kind of started the game. And he showed that the jointly by certain automorphism of IJ, that's kind of elementary conjugations, and x side will conjugate by xj, and then the signal stays fixed. Okay, so this is a set of generators, and then you have some kind of braid-like relations. Okay, that I will not explain. Maybe we'll explain them more detail next time. Perhaps not. And it has a geometric interpretation, is the group of motions of n becoming surface in S3, also the fundamental group of the space of configurations of parallel links in R3. I think there was a theorem of Brendel, Brendel and Thatcher. Okay, and then there is another one more guy here, the upper pure welded braid. This is a little bit of a tongue twister, and I call it more often the upper macro group. You look at not all the alpha IJs like in the previous presentation, but only the ones for which I is SNJ. So you take kind of half the generics and take all the other directions. Okay. So this is so we went to WP and WPN plus. Now it's again a similar product of three books. Fred Cohen with Pakenat machine and will compute the homology ring of WPN plus with two coefficients. It's exterior algebra, DD1 generators, modulo a bunch of quadratic relations. And in fact, Dan Cohen, student the time brings it, showed that this is actually a causal algebra. It's not just quadratic, it's actually it admits a quadratic of the basis. It's a causal algebra. A little bit earlier, in 2006, in a pretty amazing piece of work, Jensen, McCallum, and Meyer computed the homology ring of WPN. Okay, this was an old question of what the
Yes, there is a Zoom that we start here and we advertise it 5:30 at 4:30 and some people that are not here and will hear it. So we have to, it's not like.
Okay. Yes. Still have 2 minutes, right? So covering that years ago showed that unlike the WPN plus, this is not a tautological for any before, and this is by computer computation, an amazing computer computation. Have to go very, very deep. These groups have the same Betty numbers and SGS ranks as the hyperplane groups, and for any up to see their pairwise isomorphic. So in work with student 1 to 2020, we show this general result. If two groups are one format, or more generally filter format and optional development in the paper, and if they have different chain ranks, then the associated Braid algebras are not isomorphic. So the corollary, we show that the Braid algebra associated with the PN, WPN plus, and PN are pairwise non-isomorphic, although they have the same ranks. And we did this by computing the chain ranks by separate computations using methods of cognitive algebra. Okay, and I know Mina is pressing me. I don't know why I get in shorter times than the other speakers, but all right. Let me just. You're very stiff
1
with-
hour and 6 minutes.
1 hour and 6 minutes? Oh, I thought I started at
Later, we were supposed to start at 3:15, but you started 3:25.
Okay, all right, sorry, my bad. Okay, so I'll stop here. Thank you.